Good morning. Uh, First of all, I would like to thank the organizers for the invitation for me to present our progress on this work. So this is the title, um, and this is the outline. So only 2 or 3 things, no big deal. I will first give a excuse me, brief introduction, just an overview of quantum simulation, probably mainly for students, and then our motivation, and then I'll talk a little bit more on 1D spinor Bose gas, or we call the spinor tongues Girardeau gas, which is the model we try to realize, and then I will give you some report on the approach and the current progress, and finally the outlook. So this is for students. So today we're talking about experimentally we're using co-atoms to try to do quantum simulation for the condensed matter of many-body physics. Because this system, a closed quantum system, they're nearly defect-free, and as we have heard, talks on neutral atoms and ions. So these systems that take, for example, you start with both condensed atoms, bosons, or degenerate Fermi gas, and you can play with the mixture of them. And also they possess this internal degree of freedom, and you can control their interaction. Not only the strength, but the sign, not only that, but also the range. And you can play with the dimensionality. You could have a single potential, ring potential, double well lattice, and you could have a regular, or you could have a super lattice. For lattice sake, you can add disorder, you can engineer disorder, which you have heard from yesterday's talk. And you can even do dynamic control, say shaking a lattice. And also you could rotate, or if you don't rotate, you can use a synthetic field to generate the rotation, which you heard in the talk in the afternoon. And now people are trying to add this individual addressing capability, or so-called atom microscope. Okay, so this is a toolbox you have. For the ion part, you have a strong coupling because they're charged particle. So the particle, they are separate, farther apart. So the individual addressing is almost comfort-free. But the problem is they're distinguishable particle. But even so, you can tune the coupling graph. And we've heard from a talk yesterday that now they're going a cryogenic trap with trapping something like 100 atoms with very, very long lifetime, which gives us very optimistic hope for, say, maybe, I don't know, someday later you have a generic quantum computer running on generic quantum algorithm, then you can pretty much do everything here. Okay, so fundamental questions that can be addressed, just name a few, some hot topics, included things we're discussing in this conference, to say probing the exotic states of matter, as we have know that the Nobel Prize is announced, but this is for theory. So that's some work for we experimentalists to do. And this system is a closed system, so it's good and very, very low temperature. So it's good for studying quantum phase transition, like a quenching leading to, say, Hippo-Zurich mechanism. Depending on the quenching speed, you may not end up in the ground state, but end up with some metastable state, or you call that you have some topological excitation or state left, or you might say you have some domain left, for example. And by looking closer at the phase transition point, you can discuss the universality class of the system. Okay, and so you can also going further by studying dynamics. You can ask questions like whether the system is thermalized or it's come to some steady state, but not thermalized, which you might call that localization. Okay, so this is our motivation. So my motivation is trying to take the physical spinor condensate beyond mean field. This is my original motivation. And right now, you can see there are several ways or several things that have been discussed, which are beyond mean field. For example, spin squeezing, or entangled spin states. And for the spinor in the optical lattice, you can discuss the quantum mechanism. Yesterday we heard a talk about fermionic quantum mechanism, but the bosonic system also has its own right. Okay. All right, but then you could also take the spinor to a low dimension, say loading into a 1D or 2D traps, and you can study the topological state of matter, and also study the dynamics like we discussed. Specifically, like the 2D gas, you can look for this KT transition, and also study this quantized transport effect. It's just like a quantum Hall effect. And in the 1D case, we may call it a Latinger liquid. And Tang's-Jarut gas is a special case of this class, which taking the interaction to the limit. And it's possible that you could study the 1D spin chain and try to probe for this topological phase of this system. And finally, you could also discuss the integrability of this 1D system. So today I'll only give you our effort to realize this model. So how can we reach the strong correlation, a strong correlated regime? So normally in 2D or 3D, if the particle density is low, or it's a dilute gas, like in our case, possibly you could have particle move without interacting, or only weakly interact with the adjacent particles. And to make them a strong interact, so that they lead to strong correlation, you might can say, in our case, tuning the scattering length using Fishbach resonance, or you could load them into the 1 to 3D lattice to pin down every particle, just to simulate the case where when they're interacting, like they are bonding tightly, they don't move. On the other hand, you could also put them in the 1D track, so that particles are confined, so that they can only move along this direction. So these particles move will inevitably interact with the particles, actually all particles. So the dynamics will become collective. So you're reaching a strong correlated regime. Okay. So so what's the interesting part of this system when you go from 3D to 1D? So we can look at the particle interaction and the kinetic energy. So the interaction is simply just the collision energy times the density. And the kinetic energy in 3D, you can characterize their trap frequency, which is independent of the density. So you can parameterize this system by comparing the interaction energy and the kinetic energy. When the gamma is large, you call them a strong interaction regime. And you will find that when it's dilute or weak, or n is small, the gamma is 10 to small, so you're in a weak interacting regime. While n increases or g increases, then you can reach strong interaction. But when you go down to 1D case, the interaction form is not changed. But the kinetic energy is interesting. So this is just a very simple solution from particle in the box. Okay, so the kinetic energy is actually inversely proportional to the size of your box. Okay, and if you say evenly distribute your particle on some length L, and then the D will be L. Sorry, the length scale will be just inverse proportion to the density, which is L over N over L. That's the density. Okay. All right. So the gamma parameter again is the same, but interestingly now the gamma parameter is inversely proportional to your density. In other words, the more dilute you have you have stronger interaction, while in the dense regime instead you have a weak interaction. Another way to say is this kinetic energy turn or the quantum fluctuation actually dominates in the system. So in that case, so when the gamma parameter is small, then the particle wave function basically overlapped. So as you increase the gamma, the wave function is start to getting separate, and until a point they don't overlap, and that is where when you reach the strong coupling regime. Okay, so this model actually has been realized, but for the spinless case, and they've been realized a few years ago. This is by the Emmanuel Bloch group. No, sorry, this is by the Dave Weiss group. Sorry, which they actually changed the density. You can see by varying the density, you can tune the gamma. Well, this is the Emmanuel Bloch group, which they tune the effective mass of the lattice along this direction, which they can also reach a gamma pretty high. And this is from the Innsbruck group, where they actually tune the G, the interaction. They can tune the G to attractive. Normally, to realize this Tang-Stradu gas is saying you have a repulsive bosons to 1D repulsive boson to mimic 1D non-interacting fermions. But it has to be repulsive. But in this case, they can tune into attractive. And they found you actually are reaching some excited state, which they call super-Tang's gas. But all of these, they're talking about spinless bosons. So what's the difference if you introduce spin into your bosons? So when we talk about mimicking bosons, 1D bosons, 1D fermions with bosons, we know that intrinsically bosons they're cooperative particles, or they're symmetric under exchange of particles. So intrinsically, if you look at their spatial distribution, they may look like non-interacting fermions, but if you probe their momentum, you'll find bosons will follow this blue curve, the moment distribution, still bosonic, while for the fermionic case, you have this moment distribution up to, say, your Fermi surface. Okay. But when you have spin introduced, depending on the symmetry of your spin, you can tune such that even the moment distribution will mimic free fermions. So this is the signature we're trying to look for if we're trying to realize the system. Okay. So this is the experimental approach we're taking. So we know that atom has spins. They have roughly, these are the species that have been cooled to quantum gases. And you can characterize them into, say, hyperfine spin, which couple the electronic and the nuclear spin to give you the total atomic spin. And you have bosons and fermions. They're a SU2 group. Or you could have a pure nuclear spin. We have heard the talk yesterday talking about an SUN group, namely those atoms, their electronic spin singlet. So the spin all come from nucleus, where the scattering lengths will be degenerate in different spin states. That's why you have a higher symmetry. Or you could have pure electronic spins like chromium, dysprosium, which has a lot of electrons. Then you can reach a long range. You can have a longer range interaction. And in our case, we actually taken the most friendly one, the rubidium atoms. And the formation of spinor condensate. So this is when you turn the B field on, you will see actually the ground state spin 1 and the hyperfine excited is spin 2. These are all in the electronic ground state. Okay, so if you turn on the B field, you'll find they split into 3 or 5 states. And in the B field, only these 3 states are trappable. But in the optical trap, they are all trappable. So in this case, you use the Zeeman effect. Here, you use the Stark effect. So it can preserve the spin degree of freedom. And microscopically, their interaction is easily described by this. For spin 1 case, for the spin 2 will be additional term here. And this is the spin-independent part, or this is spin-dependent part. And the difference, or I should say the spin-dependent part actually is pretty weak. It's only about 1% of the density-dependent part. Okay. And depending on the sign of C2, if it's less than 0, then the system is minimized by lining all spins up in the second direction. So they're ferromagnetic. And when you go down to ground state, you have symmetry breaking state here. But for C2 greater than 0, you actually minimize the energy by entire lining length. So even in ground state, you don't break symmetry, rotating symmetry. Okay, so if you write down in the operator form, you can write in terms of symmetric and anti-symmetric. And you can see this binary interaction in closer detail. And interestingly, here you have this term, which you don't have in the spin half case, where 2, 0, they can annihilate and create a pair of plus and minus, or their reverse process. And here, if you take in a limit where the external degree of freedom is frozen, or they can be completely separated from the internal degree of freedom, which we call the single mole approximation, then the dynamics can be further simplified. So this is the energy contour under SMA, and specifically for the magnetization equals 0 case. For the ferromagnetic, this is the energy contour at the B field equals 0, and this is for the anti-ferromagnetic. Okay, and this is for B field, non-zero B field. So the ground state for the ferromagnetic will be here. Sorry, will be here. No. This will be the ground state here. That's the lowest energy point. But in this case, the ground state will be here. And actually, anywhere here will be, they will be degenerate. There will be huge degeneracy here. Okay. But when the B field is non-zero, then this degeneracy will be lift. So everything will contract to this point. And in this case, the atom will polarize to m equals 0 state, which we call the polar state. So this thicker line, we call it the separatrix. So what it means is within this separatrix, the phase is oscillating the finite range, but outside you have a running phase, keep going on and on. And here is where the point actually, the spin mixing almost stops. Almost stops. Okay, so it's this case. So this is the way we create our condensate. We load into an optical trap, and we can create a condensate between 20 to 40,000 atoms. The condensate. And to further manipulate the spin state, we either we can evaporate under a constant field, and the +1 state is actually the lowest energy state, and somehow we could condense almost all the atoms in this state. And if you want to push the atom in different state, we could add a gradient and move the 0 B field point out of the trap center, so you could either repel these two states out of the trap or repel these two states out of the trap. So we can, using this way to purify our spin state. To get to a richer spin configuration, we use microwave. We use multi-microwave transitions to do that. So in this case, we can actually oscillate a population in these two states, like the curve shown here. Okay, and with this state, actually, we can initiate spin mixing. So in this case, you can see that the third state is rendered through the collision of these two states. You can see clear the oscillation here. Actually, this took us quite a long time. We were very happy to see this, although there's no new physics here, but I just set some milestone in our lab. Okay, and we also study the oscillation period versus the B field, and we realized if you ran the B field, if you ran the ground state across the separatrix, you will see the period will diverge. But then we didn't see that. Then we realized actually we create a configuration where the initial phase is always pi. So we never cross the separatrix. Well, say in this paper, they actually use the radio wave to actually drive this three-level system, and they always create a spin configuration with spinner phase 0. Okay, but here we actually use a 3 microwave. We can actually directly put the population in the ground state, or in principle, we can use this to render a richer spin configuration, and we can, in principle, render the spin state with different phases and population. Okay, so up to now, to realize this system, you just need to do two things right. First of all, you need to be able to control your spin state, and second, you need to be able to put them in a 1D regime. And now I show you that spin is finally under control. Actually took us quite some time. And second, so we further load the condensate into a 2D optical lattice, which actually you create a 2D array of 1D tubes. And this just shows that while increasing the lattice depths, we can go from superfluid to insulated state. Maybe I should say that. And this is imaged along this direction, where you have a 2D lattice, and this image is from the side here or here, which you actually you see 1D case here. Okay, and this is again you can read from the superfluid to the instrument trace, and the tube direction is actually this direction. This is time of flight imaging. So the radial direction here actually expand much faster than the actual direction. And this is the dynamics we're trying to probe. The directional dynamics we're trying to probe. Okay, so once we load the condensate to the lattice, we next will ask where we are. Are we reaching the TG regime yet? Okay, so there are several ways to probe. One way to probe is by looking their say collective motion. Okay, so these are the two lowest order, lowest free energy oscillation. Say one is the zero mass mode, which all atoms or the whole cloud slashing inside the trap, or you could have this next one is the breathing mode, where the clouds contract and expand like that. Okay, and if they're free particle, say the particles are independent, then the ratio between the breathing and the common mode will be exactly twice the frequency. But in the superfluid regime, say you have a condensate or quasi-condensate here, then the ratio will be less than 2, something like that. But in the TG gas, you have an incompressible gas, and you can the ratio will again approach 2, which we demonstrate in this paper. And we also try to do that. This is the center of mass, and this is the freezing mode. And we find with different atom number loaded into a, say, 10 by 10 tubes. And by reading them out and do the ratio, we find our gamma is somewhere, in this case, approaching to 1, but not quite. Okay. And gradually we realize why. I'll try to discuss later. And we also try to detect with different way, only because the signal here is also quite noisy. So another way to detect where you're in the TG regime is the following. When the particles start to avoid each other, then the particle decay, okay, sorry. In this case, the particle decay, you have a one body loss, which is one coatom in the trap colliding with the residual gas in your vacuum chamber. That's one body loss. And you're already very cold, so you don't have a two body loss. But you have a three body loss when the density is high, or when three particles they're getting too close, then you have a higher loss rate. But when you reach in a TG regime, you have a strong suppression of your three body loss rate. So that's the idea. And we actually measure that and fitting this curve, and we can get the G3 can be suppressed by like something like 80% or so. Okay, but nonetheless, we just cannot reach in gamma greater than 1 yet. And now we gradually know that because we are compressed, I should say, the tube is not flat enough. Okay, so we're focusing too strong because lack of power. So we're upgrading our laser, and next we'll try to not focusing the laser, so to make the tube much longer, so make the landscape along the z direction flatter, and in the hope to get above gamma greater than 1. Okay. So this is basically what we achieved so far, and then we have to undergo some renovation on our system. Next, because we have toolbox hand now, and we can try to do something. First of all, we can even do spin mixing in this 1D geometry. So you can first polarize them all in the m equals 0 state, in the high field, then bring the B field, quench the B field, and then in this case, you will start to see spin mixing. And in this case, in principle, you generate a huge degeneracy on this mixed state here. Okay, and interesting question that you might can ask is, will the mixing stop? Okay, in this case, or they just keep on and on. Okay. Sorry. And next thing is, once you can add the spin degree freedom, not just n equals 0 state, but any configuration with different spin symmetry, then the next you will ask is, how can I probe the momentum distribution when they reach this spinor time schedule regime? And the easiest thing is time of flight. Time of flight is the way you measure the momentum distribution, but it may not be sensitive enough. So people have also used Bragg spectroscopy, two-bone transition, couple of motion out, so you can basically probe the momentum. But the thing is, when the tube is very flat, the frequency area will be very low. So this method will be also challenged, although people have demonstrated very, very high resolution. Third way is we might can probe by we call the focusing technique, okay, which you can, for example, this is some example, which you load your atom or you compress the atom and then slash in a trap, like in this case, and then you all of a sudden switch the trap off after some time of flight. You can resolve that, okay. So this just shows a full lattice side. You're slashing in a grand potential, and all of a sudden you switch off. You can resolve them, but instead to probe the moment distribution, you want to see when they're focused again here, and you can look. In this case, you can do a snapshot, and so that you know the moment distribution. Okay, a final remark here. So, in a theory that I described previously, it's actually a single tube physics, right? But instead, we actually have an ensemble of 1D tubes. We have about 100 tubes, and we load probably different number of atoms in there. And also you have, basically you have 100 copies of this 1D case. So you may not be able to see a beautiful plateau, like in this case, where you have only one. You have to go under some ensemble average. So Sanki Ip, which we'll talk in the afternoon, he helped us to calculate what would happen in this situation, where you actually you realize a system called spinning coherent Laminger liquid. In this case, you see you don't have a beautiful plateau, but still, when you reach in this spinor TGE regime, you will see a broader momentum distribution. And I think this is the signature we eventually look for. So to summarize, I'll give you some brief introduction how we can take spinor physics beyond the mean field, and specifically this spinor TG gas, and we report the progress, our current progress, and provide some outlook. Thank you.
So when you start to have multiple components, both gas and getting fermionized, is there some kind of effect interaction you can lead to the, for example, pairing?
Pairing? Okay, that I'm not sure. Well, you might encode it something called Holden phase, but something not easy to probe. You might can probe the say the energy gap. If this kind of phase is formed, they just look for the energy gap, I think, and then they might you might have this so-called pair. Maybe something you can comment.
I don't know exactly what's the gap. If you can have something attractive interaction, it might be.
Right, my question is whether you can induce some kind of effective interaction between these fermionized bosons, and then would that simulate some kind of pairing in the Fermi gas?
I need to have a quantum simulation for fermions.
Interactive Fermi.
Interactive fermi.
Exactly.
How do we know it's a quantum gas? What's fermion signature? Yep.
Oh, what's the signature? If you to know whether it's in the tongue strategic gas or not, like we just say, the simplest picture you can view this is when the particles start to avoid each other, which is simulating the free fermions, right? Because suppose they all spin out, and then you will find their three body loss rate decreases dramatically. You can have a strong suppression on the G3 correlation. Okay, so here, you can just by looking at the particle loss. So in other words, here you have a three body loss stronger, and the tail here, you end up with one body loss. So that's one way. And another way is by looking the probing the interaction by taking the ratio of the center of mass mode and the breathing mode. So if you're in the Thomas Fermi region, say you have super free mode, then the collective or the frequency, the breathing frequency versus the center of mass frequency will be something like this. Square root of 3. It's under 2 basically. So when it's reaching 2, you end up with an incompressible gas.
Any other questions? Okay, now let's thank the speaker again.
Thank you.